Okay, I'm recording. Any questions with the homework? Okay, then let's keep going. Okay, so no questions. Okay, so last class. Okay, so last class, we ended class with talking about theorem 1.7.1, which was all of these observations about triangular matrices, right? And taking the transposes of them, right? For instance, the transpose of a lower triangular matrix is upper triangular, and the transpose of an upper triangular matrix is lower triangular. The product of lower triangular matrices is lower triangular. Product of upper triangular matrices are upper triangular. So we have a few of these here. And so before that, we talked about triangular matrices, the effect of multiplying by, we also talked about the effect of multiplying by diagonal matrices on the left or right. We multiply a matrix on the left by a diagonal matrix, we're multiplying the rows. If we multiply a matrix on the right by a diagonal matrix, we're multiplying the columns by the corresponding elements on the main diagonal of the diagonal matrix, right? See that? D1, D2, D3, and the 3 columns. Okay, and so we talked about diagonal matrices, triangular and symmetric matrices. Okay, and so we found solutions for an equation Ax equals B. We want to find all matrices M by 1B such that the system Ax equals B is consistent. Okay, so we talked about a bunch of things, and so we're just going to continue. So this is theorem 1.7.2. It's if A and B are symmetric matrices with the same size, and if A is any, if K is any scalar, then part A says A transpose is symmetric. B says A plus B and A minus B are symmetric. And C says KA is symmetric. Okay, so reminder from last class, a symmetric matrix is one in which it equals its transpose. So a matrix capital A is symmetric if it's equal to its own transpose. Okay. And so we're saying that if A and B are symmetric matrices with the same size and K is any scalar, then A transpose is symmetric, A plus B is symmetric, and A minus B is symmetric, and KA is symmetric. Okay, this class. Okay, so so that's that theorem. And there's theorem 1.7.3. The product of two symmetric matrices is symmetric if only if the matrices commute. Okay, so matrices commuting, right? Matrices commuting means that AB equals BA, right? So when you say that matrices AB commuting means that AB equals BA. So the statement AB equals BA is equivalent to saying the product of two symmetric matrices is symmetric. Okay, and so also note that the product of two symmetric matrices is symmetric means that So the product of two symmetric matrices A times B is symmetric means that where A and B are symmetric, right? The product of two symmetric matrices A, B is symmetric means that it means that if you took AB, you took its transpose, it's equal to itself. Okay. So the product of two symmetric matrices AB is symmetric means that that equals that, where A equals A transpose and B equals B transpose. Okay, so AB transpose equals AB, where A equals A transpose and B equals B transpose, or if. So that's what this statement means. The product of two symmetries AB is symmetric. Okay, that statement means this. Okay, so good. So that's theorem 1.7.3. Theorem 1.7.4 says if A is an invertible symmetric matrix, then A inverse is symmetric. Okay. Right, so A is invertible means it has an inverse. A is symmetric means A equals A transpose. A inverse is symmetric. It's just saying that the transpose of A inverse is equal to A inverse. So note that saying that A inverse is symmetric means that if you take A inverse and you take its transpose, it's equal to itself. Okay, so A inverse is symmetric means that its transpose is equal to itself. Okay. And note that for any matrix capital A transpose and A transpose A are both symmetric matrices. Okay, so if you take the transpose of either of them, it's equal to itself. And so a proof of that, proof of the note, well, if you just take A transpose, and you take the transpose of it, but when you take the transpose of a product, it's a product of transposes in reverse order. So first you would take A transpose, and you would transpose it, and then you would take A and you would transpose it. So you have A transpose, you want to take transpose it. You switch the order, so it's instead A transpose A, but then you take the transpose of each. So it's first A transpose and the transpose of that times then A transpose. You take the transpose twice, it cancels. So A transpose transpose is A, and then that's A transpose. So I just showed us that the transpose of A transpose is equal to A. The transpose of A transpose is equal to A transpose. And so that implies that A transpose is symmetric because its transpose is equal to itself. And you can do the same thing for A transpose A. Okay, so if you have A transpose A and you take its transpose, that's equal to the transposes in reverse order. So you have A transpose A times A transpose transpose. That's equal to A transpose, and then A transpose transpose is A. And so you have A transpose A, the transpose of that equals itself. And again, that implies that A transpose is symmetric. Okay, so now that proves both of them. Okay, so that's that. Theorem 1.7.5. If capital A is an invertible matrix, then A transpose, and A transpose A are also invertible. Okay, and so you can also invert A transpose. Okay. Okay, so if A is an invertible matrix, then A transpose is an invertible matrix. And so then that means A transpose is a product of invertible matrices, which is invertible. Okay, and you can say the same thing for this. Okay, so you get that from there. Okay, so that's the end of 1.7. This next is 1.8 on matrix transformations. Okay, so in 1.1, we observed that a solution of a linear system in n unknowns, say, if you say x1 is equal to s1, x2 is equal to s2, so, and then dot, 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 xn is equal to sn. This can be expressed as an ordered triple. And the ordered triple is S1, S2, S3, dot, 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 Sn. Okay, so we can represent a solution of a linear system by an ordered n tuple, right? Where the number is telling you which unknown is that value is assigning. So the assignment where x1 is s1, x2 is s2, and so forth, xn is sn. S1 being the first coordinate means that's the value you assign to x1. S2 being the second coordinate means that's the value you assign to x2. Dot, 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 Sn is the last nth coordinate, which means that's the value assigned to last variable xn. Okay, and so that's a concise, fast way to tell the reader what you're assigning each unknown in your solution. Okay, so reminders. So a two-tuple is an ordered pair. For instance, A comma B would be an ordered pair, right? A three-tuple is an ordered triple. For instance, A, B, C. Right, so that would be an ordered triple. Also, saying that A comma B as an ordered pair is equal to C comma D is equivalent, or if that equation is true, if and only if A equals C and B equals D. Okay, so what that means is that two ordered pairs are the same if and only if their first members are the same, A equals C, and their second members are the same, B equals D. So if their first members are the same and their second members are different, that means they are not equal as ordered pairs. Okay, so for instance, if you had 1 comma 2, that does not equal 2 comma 1, right? Because you could say either the first members are different or the second ones are different. Okay. The set of all n tuples of real numbers is denoted by R to the n. Okay, so the set of all n tuples of real numbers is denoted by Rn. The elements of Rn Okay, so I think you can see my screen. Just good. Okay, the internet sometimes. Okay, the elements of Rn are called vectors and are denoted in boldface type, such as A, B, B, W, and X. I'm going to add the bold. So let's see. B. Okay, so these are representing vectors in Rn, and they're denoted using boldface to differentiate them from things that are not vectors that are not in boldface. Okay. So if you have, let's say, a column vector like this, okay, so then that can be used instead of the ordered n tuples. So that can be used instead of S1, S2, S3, dot, 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 Sn. Okay, so they're both just ordered lists. This is a list of n things, and this is also a list of n things. They're just two different ways to illustrate the same exact thing. Okay, and so I'm denoting this by 2. I'm not multiplying by 2. I'm just denoting it as 2. And I'm denoting this by 1. And I'm not multiplying it either. So that way, the left-hand notation, I'm calling this 2, and I'm calling this 1. Okay, so 1 is called the comma delimited form. 2 is called the column vector form. Okay, so each have a name. So this is the comma delimited form, and this is the comma vector form, column vector form. All right, new idea. Okay, so for each I from 1 to n, let little e sub I denote the vector in Rn with a 1 in the ith position. And 0 everywhere else. In column form, these vectors are, so for instance, E1 would be the column vector in which there is a 1 in the first position and 0 everywhere else. So copy this. There's a 1 in the first position. So we're living in Rn, so I'm going to put a dot, dot, dot there. So there's going to be n rows of that column vector. E2 is now there's going to be a 1 in the second position and 0 everywhere else. E3 is the column vector, a 1 in the third component and 0 everywhere else. There's still zeros everywhere else. The dot, dot, dot is just saying the zeros everywhere else before the last one. And then the nth one, E sub n is equal to Well, if there's zeros everywhere else, except the nth one is a 1. Okay, so then this is the notation for E sub I. That's explaining this. Okay, so this thing in blue is describing all of that. Okay, so that's E sub I denote the vector in Rn with the 1 in the ith position and 0 everywhere else. E1, 1 the first, E2, 1 the second, E3, 1 the third, En, 1 in the nth, and the ones in between, and the zeros everywhere else. Okay, so that's what that notation is saying. So we're going to let the EIs, E1 to En, be those vectors. We call the vectors E1 ... to En, all of them together. We call E1 to En the standard basis. Sorry, we call each one the standard basis vectors for Rn. Okay, so for example, okay, so they're each standard basis vectors for Rn. All of them, E1 to En, those make up the standard basis vectors for Rn. Okay, so for instance, if you had E1, which was equal to, okay, which is equal to 1, 0, 0. You had E2, which is equal to 0, 1, 0. And you had E3, which is equal to 0, 0, 1. For example, those three vectors are the standard basis for R3. Are the standard basis vectors for R3. Okay. So these three make up the standard basis vectors for R3. R3 because these are all vectors in 3 space, right? The space of all vectors with 3 components. Okay, 1, 2, 3. The components are the number of things in them, right? So R3 is the space of all vectors with 3 components in them. And these 3 specifically together are the standard basis vectors for that space R3. The vectors E1 ... to En in Rn are termed basis vectors because all other vectors in Rn are expressible as are expressible in exactly one way as a linear combination of them. Okay, so the vectors E1 to En have this special property and are called basis vectors. The special property is that all vectors in Rn are expressible in exactly one way as a linear combination of them. Okay, and to explain that, for example, if you take an arbitrary vector in Rn, meaning a vector with n components, and you call it x. So this arbitrary vector x in Rn are going to have components x1, x2, x3, ... xn. So this is an arbitrary element of Rn. Then we can express x as, so we can express x as equal to x1 E1 plus x2 E2, that's E2, plus x3 E3 plus dot 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 plus xn en. Okay, this can be a little confusing. The e's are vectors. E1 is a vector, E2 is a vector, E3 is a vector, E4 is a vector, dot dot dot, En is a vector, right? All the e's are vectors. The x's, the x1, x2, x3 to xn, these are numbers. These are components of the vector x. Okay, so we took an arbitrary vector x in Rn, and we're expecting S as a linear combination of E1 to En, meaning it's a linear sum of the vectors E1 to En. A linear sum of the vectors E1 to En is taking each of them, multiplying them by a constant, and adding those products. Okay, so we're expressing x as a linear combination of E1 to En by multiplying each of those vectors by a constant and adding up those products and getting equal to x. Okay, and so what this is showing is that for any arbitrary vector x in Rn, we can express it specifically as a linear combination of E1 to En in this way, that x is equal to that linear combination. Okay, and actually, this is the only way to express x as a linear combination of E1 to En. Okay, so not only can we express x in this way, it is the only way to express x as a linear combination of E1 to En. Okay, that's because E1 has a 1 in the first coordinate, right? E1 has a 1 in the second, E3 has a 1 in the third, En has 1 in the nth. There's zeros everywhere else. So if I were to multiply this by a constant other than x1, the first component would have a number different than this first component. And all of the other members of the sum, all the other elements of the terms in the sum, they have zeros in the first coordinate, because these vectors all have zeros in the first coordinate. E2 is a 0 in the first coordinate, E3 to En. And so you multiply a vector with a 0 in the first coordinate by a constant, it's always going to have a 0 in the first coordinate. So all those terms have a 0 in the first coordinate. And so x1, E1 has x1 as the element in the first coordinate. And so when you add all these up, you only have x1 as the first coordinate. So there's exact correspondence between members of this vector x and the coefficient next to each e. And so if they all match exactly these, then x is equal to this. And if they don't match exactly, then your linear combination will not equal x. So so not only is x expressible as a linear combination in this way, it is the only way to express x as a linear combination of E1 to En. Okay, so the exactly one way part is very important. Okay. Okay, and so that's what makes these basis vectors special. That's why they're called standard basis vectors. Well, that's why they're called basis vectors. Okay. Just standard, just basis vectors. Okay, definition. A function is a rule that assigns with each element of a set A one and only one element in a set capital B. If F associates the element B with A, then we write F of A is equal to B. And say B is the image of A under F. The subset of the codomain that consists of all images of elements in the domain is called the range of F. Okay, so there's a lot of things being defined here. I just want to put this here. Okay, so a function is a rule that assigns with each element of a set capital A one and only one element in a set B. If F associates the element B with A, then we write F of A equals B and say B is the image of A under F. The subset, I'm going to write some stuff on the whiteboard that explains. The subset of the codomain that consists of all images of elements in the domain is called the range of F. So we have a whole bunch of definitions here. Okay, so this is the range of F. There's a definition there. So what we're going to do is copy this definition and go to the whiteboard. Okay, so so a function is a rule that assigns each element of a set A one and only one element in a set B. So for instance, I'll give you an example of a function. This is called an arrow diagram representation of a function. So if A is your domain and B is your codomain, as we're calling it, what I'm drawing is a picture F. We're drawing a function F from A to B. So for instance, if set A consisted of the numbers 1, 2, and 3 only, this was the entire set A, then the function F would map each of them to the set B. And so let's say the set B contains the letters little a, little b, little c, and little d. And so I'm going to assign each number to the letter in the alphabet, the letter that has that number has its order. So 1 goes to A, 2 goes to B, and 3 goes to C. And so this F, what F does is it maps 1 to A, 2 to B, and 3 to C. And 1, 2, 3 are in set A, and A, B, C, D is in set B. So this F is a function, is a rule that assigns with each element of a set A one and only one element in the set B. So notice how 1 is assigned one and only one element in set B. It's assigned little a. So 1 is assigned only little a. So 1 is assigned one and only one element in set B. 2 is assigned to little b. 2 is assigned to one and only one element in set capital B. 3 is assigned to C. 3 is assigned to one and only one element of set capital B. So every element of this set capital A, each element of a set capital A is assigned one and only one element in a set B. So this arrow diagram is an illustration of a function F, which satisfies the definition of a function. And so F is a function. Okay? It assigns to each element of a set A one and only one element of a set B. So the second sentence says if F associates the element B with A, then we write F of A equals B. In other words, if we can write F of 1 equals A, because we associated 1 with A. See that? F maps 1 to A, so F of 1 is equal to A. And what we would say is if you read this, it would say A is the image of 1 under F. So that equation I wrote above it, F of 1 equals A. So that is read F of 1 equals A. But then you could also say, there's a lot of things you could say. You could also say the image under F of 1 is A. Okay, so that's end quotations there. And then you can change the order. You could say A is the image under F of 1. Okay, so these are all different ways to say the exact same thing, that one equation above it. Okay. The next sentence says the subset of the codomain that consists of all images of elements in the domain is called the range of F. So what I'm going to do is I'm going to label this subset of B there. You see that pink, is it pink? Yeah, that pink subset consisting of A, B, C, that's the range of F. So this is the range of F. So the range of F consists of all the images of elements in the domain. Okay, the image of 1 is A, the image of 2 is B, and the image of 3 is C. So the set of all images is A, B, C. Okay, so the range here, the range is equal to the set A, B, C. It's the set of all images. It's the set of all images of elements of all images under F of elements in set A. So this is the range of F. Okay, set A is its domain. And so if you take the images, the set of all images under F of elements in the domain of that function, you get the range. So here, the range of F is A, B, C. See how D, nothing, it gets mapped to D. So D is not in the range of F. Okay, so that's an example of the range of F. So this is a definition of a function, of a range, of codomain of F. Okay, so here B is the codomain. And here A is the domain. Okay, so A is the domain, B is the codomain. And so then this is definitional instead. Okay, so I said what the I'm going to say, okay, the set B is called the codomain. The set capital A is called the domain. Okay, so set capital A is called a domain. Set capital B is called the codomain. Okay, and so we have 4 definitions there. Yes, it's a loaded definition, very important. So I'm going to label this as very important. Okay, in mathematics, this is used. It's extremely important in mathematics, a function. Okay, so that's the definition of a function. In fact, I'm going to capitalize it. I mean, not make it bigger. Okay, so that's the definition of a function. Another definition. If F is a function with a domain Rn and codomain Rm, then we say that F is a transformation from Rn to Rm. Or that F maps from Rn to Rm, which is denoted by writing so F from Rn to Rm. In the special case where m equals n, a transformation is sometimes called an operator on Rn. Okay, so F is a transformation from Rn to Rm. That's what this definition is about. Okay, and so this is the notation saying F is a function whose domain is Rn and whose codomain is Rm. Okay, it's not saying the range is Rm, it's saying the codomain is Rm. Okay, so this map does not have to map to every element of Rm. It just has to map to a subset of Rm. And when m equals n, when you're mapping one space Rn to the same space Rn, then you can call this an operator on Rn. Okay, so new idea. Suppose we have the system of linear equations. And so this system is W1, which equals A11 x1 plus A12 x2 plus A13 x3 plus dot 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 plus A1n xn. And so W2 equals A21 x1 plus A22 x2 plus A23 x3 plus dot 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 plus A2n xn, and then dot dot dot, and then the last one is Wn is equal to A n1 x1 plus A n2 x2 plus A n3 x3 plus dot 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 plus Ann x n. Oh, but this is sorry, this is m. Okay, so we have m equations and n unknowns. The first indice is telling you which equation you're in. So this one is for first equation. That's why there's ones here. And then the first indice here is a 2 because they're on the second equation, right? The last equation is the mth one because it's W1 to Wm. So the first indice in all of them is an m. But now the second indice is saying it's a coefficient of which unknown. So it's the second one's a 1 because it's next to x1. The second one's a 2 because it's next to x2. This is a 3 because it's the second component is a 3 because it's next to x3. The second component is an n because it's next to xn. Okay, and you follow that for all the equations. Okay, so you have a system of linear equations represented in this way. And so which we can represent using matrix notation as the following. So you can, instead of writing it as an equation, you can write it using matrix notation. And so that matrix notation is W1, W2, W3, dot, 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 Wn, and that's equal to the coefficient matrix times the other matrix. So I'm just going to You have a 5 by 5 matrix. So just A11, A12, A13, dot, 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 A1N, A21, A22, A23, dot, 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 A2N, and this is A31. To use my mouse. A32, A33, dot, 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 A3N, and then everything's dot, dot, dot here. So it's dot, 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 dot. And this is A, oh, this is an M. So this is A M1. This is A M2. This is A M3. Dot, dot, dot. A M N. Okay, so that's the coefficient matrix. And then you multiply that by the unknown matrix. So this is the matrix of unknowns. And so that's going from X1 to Xn. Okay, and so you can represent this linear system of equations using this one matrix equation. Any questions about anything so far? Set the plug in my charger. For a second. Okay, so, or you could write this more briefly, as AX or W equals AX. Okay, so W is this matrix, right? Capital A is this coefficient matrix, and little x is that matrix there, including the brackets, not just the entries. Right? So, so you can express this entire thing as this one matrix equation, W equals capital AX. As long as you stick with convention, and all of these three things mean these matrices. Okay. Okay, so we have a compact way of expressing that entire linear system with one short matrix equation, as long as we stick with the notation, conventional notation the entire time. Okay, so I'm going to call this 5 for my own reason. So, so I'm calling this 5. Okay, so because I'm kind of following the book, so the book called it 5. Okay, so we will view. So okay, so you can view 5 as an abbreviated version of the other one, which is 3. Okay, so you can call this entire system okay. So we're going to that system is denoted by 3. Okay, so we can view 5 as an abbreviated version of 3. It can also be viewed as a transformation that maps vector x in Rn into a vector W in Rm by multiplying x on the left by capital A. Okay, so this is an abbreviated version of this whole thing. But also you can think of it as if you take a vector little x in Rn, any vector little x in Rn, you can think of this equation as taking this little x in Rn and sending it to this W in Rm by the rule that you, in a sense, that you take this vector x and you left multiply it by A to get W. Okay, so 5 can be seen as a transformation that maps any vector little x in Rn to a vector W in Rm by multiplying x on the left by matrix A. Okay, so on the whiteboard, let me illustrate that. So if you have W equals matrix capital A times x, then you can think of this equation, right? We're thinking of this equation in a sense as being a transformation, where as an input, we input the vector x, and as an output, we input the vector W. But the function is left multiply by the matrix capital A. So the function is left multiplied by capital A. So if you input x into it and you call the output W, then the output W has to be taking x and left multiplying it by A to W equals AX. So that's how this function is described by the equation W equals AX. Okay, so this equation is also can be expressed as a function for every x in a vector space Rn to a vector W in Rm. Okay, and then a common notation for a function that sends elements of one space Rn to another space Rm is this notation, f colon Rn to Rm. It's taking arbitrary vectors in Rn and mapping them to Rm by the rule left multiplication by matrix A. Okay. Okay. Okay, so we call this a matrix transformation, or matrix operator, where when m equals n. Yeah. So we call this a matrix transformation. It's a matrix transformation because it's a transformation obtained by multiplying by a matrix. Okay. So it is called a matrix transformation because the function is described by left multiplying input vectors by a matrix. Saying operator instead of transformation is just for when the Rm equals n. So then that would be mapping vectors in Rn to Rn. Okay. Okay, so we denote it by a matrix transformation by T sub A colon Rn Rm. Okay, so T sub A is a matrix transformation that maps vectors in Rn to vectors, corresponding vectors in Rm by the rule that you take the vector x in Rn and left multiply it by the matrix A. So the A in the subscript is telling you what that matrix is that you're left multiplying to define this equation or to define this transformation, matrix transformation. Okay? If I had T sub B here, then the matrix that you left multiply would be B, where if you're given A and B, then it would be a difference between left multiplying by A or B. Okay? Okay, so I'm going to draw a picture illustrating this. Okay, so if you have your space Rn, and you take a point in that space Rn. Okay, so a point in a space is just one of the elements of the set, right? So an x in Rn is an n tuple, a vector with n components. Okay, so we're going to take that point x in Rn. Okay, we're going to take that x in Rn and we're going to map it to a corresponding element in Rm by this rule. So what we're talking about here is T sub A. So T sub A is going to send an arbitrary element x in Rn, and it's going to map it to, I'm just going to use the normal notation, T sub A of x. This is the notation of mapping an element x by the function written to the left of the parentheses, right? So if this function was f, it would be f parentheses x. Because the function is called T sub A, it's T sub A parentheses x. Okay, and so this is illustrating a function T sub A that I was just writing on the whiteboard from Rn to Rm. Okay, so this notation is just illustrating the idea that this function, this matrix transformation, is mapping an element in the domain to an element in the codomain, right? So this Rn here corresponds with this Rn, right? And this Rm corresponds with this Rm there. So we're just taking elements in Rn and they're being mapped to something in Rm. So that's the explanation of this notation here. T sub A colon Rn to Rm. The T sub A is just the name of the function. T sub A is the name of the function, and it's a function with that name that maps arbitrary points in Rn to points in Rm. Okay, this notation though doesn't fully describe the function. Okay, so this notation is not meant to tell you exactly what the function is. It's telling you information about the function. It's not completely describing the function. So this notation T sub A from Rn to Rm, it's just telling you the domain and codomain and the name of your function. You don't know where these points are going from that notation. Okay, so there might be an equation that tells you the rule that defines the function. And so this is just a quick way of giving you other information, okay, about the function, some of the information. Okay. Okay, so in situations where we're specifying the domain and codomain, is not essential, we will express this is 4. So I'm going to do what I did the other time. That's 4. That matrix equation is 4. Okay, so this is equation 4. So what we're going to do is talking about that one. So in situations where specifying the domain and codomain is not essential, we will express 4 to express this matrix equation. As W equals T sub A of X. Okay, and I'm going to put a 6 here, denoting a 6, and not multiplying by 6. Go, good. Okay, and so this is the function T sub A, the matrix transformation T sub A. It's taking any x in Rn, left multiplying it by the matrix A, and getting the vector called W in Rn. Okay, so we call the transformation T sub A multiplication by A. Specifically, we mean left multiplication by A. Okay, so you don't have a choice. You don't have a choice between left or right. It has to be left. Okay, so multiplication by A, for our purposes, we mean left multiplication by A, not the other way around. Okay, so we can also express 6 in systematic form as so x right arrow W. We're above the arrow. Let me see if I can. See if I can do this on Word. So the T sub A is directly above the arrow. Okay, so the T sub A is directly above the arrow. So T sub A is a map from X to W. The T sub A is directly above the W. I'm denoting this by 7. Okay, so the 7 is just denoting it, not part of the notation. That's the notation. Okay, so in systematic form, it's just saying that T sub A is a function whose inputs X and whose outputs are W. Input X, output W. So this is the exact same thing as this. It's just a different way of saying it. Okay, so I think it's easy to see how that could mean that, right? Okay. So you don't have to get stuck on equations. You can. There's more than one way to express things. This is a way of expressing something using an equal sign, and this is the way of expressing something using an arrow. Okay. Correctly. Right? Okay, so this is the correct way to use an arrow to express this equation conventionally. Okay. And so, which is red. So that arrow 7, this whole thing. So what this is red is that it's red T sub A okay is red T sub A maps X to W. Okay, so this is red T sub A maps X into W. Okay, example 1. Okay, so the transformation from R4 to R3 defined by the equations W1 is equal to 2x1 minus 3x2 minus 5x4. W2 is equal to 4x1 plus x2 minus 2x3 plus x4. W3, I just have to type this fast. W3 is 5x1 minus x2 plus 4x3 So we have a transformation from R4 to R3 defined by those equations and be expressed in matrix form as, so we can express this in matrix form. Let me just, okay, so this would be W1, W2, W3. So you're going to equal a 3x4 matrix. Times a 4x1 matrix. It's going to be 2, -3, 0, -5, 4, 1, -2, 1, 5, -1, 4, 0. Okay, and then this is x1, x2, x3, and x4. Okay, so we can express this linear system in matrix form in this way, right? So you can see how the W's match, and there's 4 unknowns, x1, x2, x3, and x4, they go there. And then you can see how these coefficients, these numbers match up with these coefficients here on the right-hand side of each equation, right? 2, -3, 0, -5, and so on. Okay, now why does this linear system represent a transformation from R4 to R3? Well, if you look at this matrix equation, you can see that as an input, you have 4 unknowns, x1, x2, x3, and x4. And as an output, you have 3 unknowns, w1, w2, and w3. So the input, remember, we think of a matrix transformation as left multiplication by matrix A. So here, the matrix A is that matrix I'm highlighting. It's that coefficient matrix. So we're inputting this 4 tuple, x1, x2, x3, and x4. And the output is this 3 tuple, w1, w2, w3. And the function is left multiplication by this matrix A. This A equals that coefficient matrix. So again, we have a matrix transformation, meaning a function defined by left multiplication by this matrix A, or a coefficient matrix of this linear system, where the input is this vector in R4, and the output is this vector in R3. And so you can again see this linear transformation as this matrix equation, and this matrix equation is illustrating how you can think of this linear system having inputs 4 vectors and output 3 vectors, especially the matrix transformation left multiplication by that matrix. Okay, so that's why it's a transformation from R4 to R3. Okay, so from that, from that equation, from which we see a transformation it's a transformation of left multiplication, because when we say multiplication, we mean left multiplication. So from which we see a transformation of left multiplication by the matrix A, which is equal to this matrix, just left multiplying by that matrix. Oh, sorry. Get rid of that. Okay, so we're left multiplying by that matrix A. So this is a transformation from R4 to R3. Inputs R4, output R3. Any questions about any of this? Okay, so that's that. If our vector x that we input into this matrix transformation is this specific four tuple that I'm going to put in now. So if our four tuple input is 1, -3, 0, 2. So if x is that function, then what we have is that our vector here, right? Now that vector is equal to t sub a of x, because t sub a of x is left multiplication of this vector x by a, right? And so in order to get this output vector, we need to take the input vector as this. You need to take that as this input vector and then left multiply it by that matrix A. And so that's t sub a of x, right? And so t sub a of x, again, is ax. And A is equal to this matrix. And x, the input vector that we chose, is that matrix. And so you just have to multiply those two things. Okay, so if you multiply those two things, you can think about the size of this matrix. Well, the size of that matrix is 3 by 4. And the size of this matrix is 4 by 1. So the resulting matrix, since the inside entries are both 4, they're the same, you can multiply them, and then the size of the product is determined by the outer entries, and so the product is 3 by 1 matrix. So you have a 3 by 1 matrix there. And so what I want is a column vector with 3 components in it. So I have a vector like that. And so now you can just find each entry by multiplying these two matrices and getting each entry one at a time. So to find this top entry, you would take 2 times 1 plus -3 times -3 plus 0 times 0 plus -5 times 2. When you add those products, you get 1. Okay, you get 2 plus 9 is 11 plus 0 plus -10. So you get 11 plus -10, which is 1. Take the next sum of products, 4 times 1, which is 4, plus 1 times -3. 4 plus -3 is 1. -2 times 0 is 0, so you still have 1. And 1 times 2 is 2. 1 plus 2 is 3, so you get 3 here. Yeah, 3 there. And then you take each entry in the third row, multiplying correspondingly by the entries in this column vector, and then add the products to get this entry. So it's 5 times 1 plus -1 times -1 plus 4 times 0 plus 0 times 2. That's 5 plus 3 plus 0 plus 0. That's 8. Okay, and so what we did was we found the components of the output vector. We found that W1 equals 1, W2 equals 3, and W3 equals 8, because this 3 by 1 vector is equal to this 3 by 1 vector. The only way two matrices are equal is if if corresponding entries are all the same or all equal. So that means that W1 has to equal 1, and W2 has to equal 3, and W3 has to equal 8. Okay, so what we did there was find the output of this matrix transformation when our input is this x. Okay, so we just plug that into our matrix transformation, our matrix function, to get this output. Okay, so we found above that t sub a of this input vector, instead of writing x, I'm going to write, you wouldn't necessarily always abbreviate, you'd probably put x there, but I just want to illustrate the output is then this vector. Okay, so for our t sub a matrix transformation, when we input this vector, we got us an output that vector. Okay, and notice that the input and output vectors don't have to be the same size. Okay, the size change is determined by the size of the matrix A that you left multiplied by. Okay, so that's example 1. Example 2 is if 0 is equal to the 0 matrix, the 0 m by n matrix, then T naught of x is equal to left multiplication by the m by n matrix 0. And that's equal to 0. But again, I went over this another day, how you have to take into context the meaning of a 0, right? In numbers, when you're using numbers, 0 is just a quantity 0, right? When you see the symbol 0, it only means one thing, the number 0. But in matrix notation, a 0 can actually represent any of infinitely many sized matrices, okay? So a 1 by 1 0 matrix is just a 1 entry matrix with a 0. A 10 by 10 0 matrix is a 10 by 10 matrix where all the entries are 0. So each of these zeros are 0 matrices of possibly different size, okay? And so how do you know the sizes? Well, first, it was given to you that the 0, it was given to you that the 0 matrix is an m by n 0 matrix. And so what that means is it's the first 0 here, okay? So this is an m by n 0 matrix, this matrix right here. Okay, so you have an m by n 0 matrix, that's 0. That T naught, that 0 is still the m by n. It's the same m by n 0 matrix that was given to you in the if part, this one, okay? So that's an m by n matrix, and this is also an m by n matrix. Now, when you output it, what's happening is that you're multiplying this m by n matrix by x. And so x here is an n by 1 matrix. Okay, so x is an n by 1 matrix. The inner entries are the same, and so you can multiply the two together. But the output vector is an m by 1. So this matrix is m by 1. So even though the symbol 1 is being used 3 times, the first 2 times it's m by n, and then the last one it's m by 1. The reason why it changes here, which may be confusing, is that first you're given that 0 is the m by n 0 matrix. And so we initially talk about 0 here. And so that is the m by n 0 matrix that we said. Here, we didn't change this matrix. T naught of x is just left multiplying by that 0 matrix. So this equal sign had nothing to do with no change occurred to that matrix with that equal sign and that argument. So 0 is still an m by n matrix. But when you left multiply x by 0, multiplying by a matrix can change the size of a matrix. And in this case, it does. And so that's when you now divert from the assumed 0, right? Our notation said that 0 is of this size. But when you do something that changes its size, you've now left the original meaning of 0, and now it's an m by 1 0. Does that make sense? But you don't have to say at every step of the story what the size of your 0 matrix is, because if you just say what is at the beginning, by following the steps, you know not only what it is at the end, but you know every step of the journey what 0 was in between. So every 0 is clearly defined by saying what 0 is initially. Okay, so I'm making a long explanation of this because it can be confusing for people, right? The idea behind here is that the writer doesn't want to write in the size of the 0 matrix every time he or she refers to this matrix, right? And so the solution is tell the reader what this matrix is initially, and then by following the steps of the proof, you can know how the initial thing changes step by step, and so you can get rid of the annoyance of writing all the subscript notation, and it's much easier to read. It's much easier to read that than is to see subscripts everywhere denoting each size. Okay, it's probably easier to understand with the subscripts, but in terms of presenting information to the reader, if everything was written with all this notation everywhere, it would be harder to read the page. Okay, but anyway, so that's the idea behind that. So that's why that happens, and that's to avoid you getting confused about change in the meaning of 0. Okay, so multiplication by 0 maps every vector in Rn into the 0 vector in Rm. So we call this the zero transformation from Rn to Rn. Okay, so this is the zero transformation from Rn to Rm. And again, multiplication means left multiplication. Okay, so I'm just adding what is happening. It is left multiplication, and we're saying multiplication for short for left multiplication. Okay, when you multiply a matrix, something by a matrix on the left and right, different things can happen. And so you have to, so there has to be a specification over what multiplication you're choosing, and we're choosing left. Okay. If you're multiplying all your vectors on the left by zero of an appropriate size zero matrix, the result has to be a zero matrix. Okay, that's why it's called the zero transformation from Rn to Rm. Okay, there are lots of zero transformations, right? If you change the size of the domain, if instead of R2 to R3, you say R3 to R2, right? So you can change the sizes of your domain and codomain, but you'd still call it a zero transformation because it's sending all the vectors in your domain space to the zero vector of your codomain space. Okay, and if you change the codomain of your space, of your function, then technically the output vectors are different. Even though they're all zero vectors, they're zero vectors with different number of components. Okay, so just because we're referring to something as the zero transformation, there are infinitely many zero transformations where each one can have a different domain and a different codomain. And the outputs, even though they're all zero, they're zeros with different number of components, right? So the output is always zero vectors, but those zero vectors can be of different sizes for different zero transformations with different codomains. Okay, if that makes sense. It's a little confusing. Okay, so example 3. If I equals to the m by n identity matrix, which equals to I sub n. Oh, sorry, n by n identity matrix. Okay, so an identity matrix is a square matrix. And so when you refer to an n by n identity matrix, it's abbreviated I sub n because you're just repeating the number of rows, columns, right? It's redundant to say an identity matrix has n rows and n columns. Once you know it has n rows, it has to have the same number of columns as a square matrix. So I sub n suffices to completely describe the size of an identity matrix, okay? Then, but keep in mind, if your matrix is not square, then you may need to specify the number of rows and columns. Okay. So then, if that's true, I equals in, then t sub I of x is equal to ix, right? Because it's left multiplication by this matrix there, right? That's what the matrix transformation does. It takes your input vectors and left multiplies them by a particular fixed matrix. In this case, it's I. That I is because the subscript I is there. That's where it's telling you what matrix you're left multiplying every input vector by. So t sub I of x equals ix, and when you multiply by an identity matrix, you get the same vector back. So ix equals x. Okay, and so multiplication by I, and I still mean left multiplication. So left multiplication by I maps every vector in Rn to itself. Okay, so we call t sub I the identity operator. on R n. Okay, it's the identity operator on Rn because it takes every vector in Rn and it maps it to itself. That's what identity does. It maps up things to itself. Okay, on Rn because the domain is Rn. Okay, so next is theorem 1.8.1. For every matrix capital A, the matrix transformation T sub A from Rn to Rm has the following properties. For all vectors u and v, and for every scalar v. Okay, sorry. A, T sub A of 0 is equal to 0. B, T sub A of K U is equal to K times T sub A of U. C, T sub A of U plus B is equal to T sub A of U plus T sub A of B. And D, T sub A of U minus V is equal to T sub A of U plus T sub A of B. I mean minus. Okay, so for every matrix A, the matrix transformation T sub A from Rn to Rm has the following properties for all vectors u and v in Rn, because it's in the domain. It doesn't need to be said, but I'm just adding it so that you know. So those are elements of that. So it's in Rn. In Rn, and for every scalar k. Remember, a scalar is just a constant. In this case, it's an element of real numbers. So, right, so scalar here means a real number. Okay, so scalar k means that k is a real number. Okay, so A, T sub A of 0 equals 0. B, T sub A of ku equals k times T sub A of u, and then the other two, right? So here the plus corresponds to this plus, and here the minus corresponds to that minus. Okay, as a note, if you take T sub A of K1 U1 plus K2 U2 plus plus KR UR, that's equal to K1 T sub A of U1 plus K2 times T sub A of U2 plus KR T sub A of UR. Okay, so you can see how see how these are similar, right? We're just taking, instead of T sub A of the sum of products, it's T sub A of it's the sum of T of A of each term. So it would be T of A of this product plus T of A of this one plus dot plus T of A of that one. And because of B, the constant inside the parentheses can move outside of it. And so when you think of T of A of the sum as T of A of each separate term and adding those, each time you can move the constant out. So you get K1 T sub A of U1 plus K2 T sub A of U2 plus dot plus KR T sub A of UR. Okay, so we have this equation for any input of T sub A. Okay, and so this is denoted by 10. Okay. Next is theorem 1.8.2. T from Rn to Rm is a matrix transformation if only if the following relationships hold. All vectors u and v in Rn, and for every scalar k. So property one is that T of u plus v is equal to T of u plus T of v. Property two is that T of ku is equal to k times T of u. Okay, this is called the additive property. This is called the homogeneity property. Okay, you don't need to know that for the exam. Okay, so so you have this one property called the additive property, and this other property, the names you don't need to know. You need to know these rules. Okay, so this is called the homogeneity property. This second one is saying that you can move the constant out, and this is saying that you can think of it like that. Okay, so a transformation that satisfies the linearity conditions 1 and 2 in theorem 1.8.2 is called a linear transformation. Theorem 1.8.2 can be rephrased as the following. Okay, but just before I go there, I'm just saying when you have a transformation T from Rn to Rm and both of these things hold, then you can conclude that it's linear. Okay, so these two properties define a linear transformation. So when your transformation satisfies, again, these two properties, it's called a linear transformation. So this theorem can be rephrased as the following. Theorem 1.8.3. It says every linear transformation from Rn to Rm is a matrix transformation. And conversely, every matrix transformation from Rn to Rm is a linear transformation. Okay, so that, to help you understand what I'm saying here, right, remember a matrix transformation, these are notes about above, okay? So if you have a matrix transformation, right, you might think of that matrix transformation as something like T sub A of X, right? Left multiplication by A. That would be a matrix transformation. And it could be a matrix transformation from Rn to Rm, right? When you think of a linear transformation, you're thinking of a function that satisfies the two properties above. So that would be a function satisfying properties 1 and 2 above. Right? So that would be a linear transformation. Okay. So what theorem 1.8.2 is saying is that the relationship between matrix transformations and linear transformations is that every matrix transformation is a linear transformation, and every linear transformation is a matrix transformation. Okay, so theorems 1.8.2 and 1.8.3 are saying that every matrix transformation is a linear transformation, and every linear transformation is a matrix transformation. Okay. All right. So this is exactly those words, but that's what this theorem is also saying. When you have a matrix transformation T, you know that it satisfies these two properties, which define a linear transformation. Also, if you have a function that satisfies these two properties, meaning it's a linear transformation, then you can conclude it's also a matrix transformation. Okay, so all of this confusingness here is just saying that you have matrix transformations and linear transformations, which are functions that satisfy those two properties, and that each is the other. Every matrix transformation is linear, and every linear transformation is matrix form. Okay, that's what all of that is saying. Okay. Okay. Okay, so I'm just going to illustrate something. When you have a transformation from Rn to Rm, right? You could depict it in two ways. You could think of it. There's two different viewpoints of the same thing. You're talking about the same thing, still just from a different viewpoint. So you could either say, okay, I have elements in Rn, and I'm mapping them to elements in Rm, but I could think of them as vectors in Rn. So if this was the origin in n space, I could think of x as a vector, right? Where x is a vector starting at 0, right? So the tail is where it starts and the tip is where it ends. So you can think of x as a vector whose tail, the beginning, is at 0. Okay, so you have a vector x there. And so then we can map that to a vector in Rm. Rm is the space with the 0 vector, like the origin, right? And then you have another vector here. And so this is a vector whose, again, the tail is the beginning, it's at 0, but the tip is at a point, and that point is like the name of the vector, but it's also like where the vector is at that tip. So we call this vector t sub a of x. And so the input and output points are not just points, they're actual vectors themselves. So this function t sub a is mapping vectors to vectors. So one viewpoint is that you're mapping vectors to vectors. So t sub a maps vectors to vectors. Okay, so t sub a maps vectors to vectors. Another viewpoint, and you're talking about the same thing, just from a different viewpoint, is that instead of thinking of it as mapping vectors to vectors, you can think of it as mapping points to points. So, so that's your domain still in Rn, and we're talking with the same function. Then, if you took 0, right? Let's say 0 would map to 0. So 0 maps to 0. But then you can have a point X where X is an n tuple, right? It's an element. It's a point in the space and it's an element of it. So X itself is not a number. It's an n tuple living in Rn. And so then this function, t sub a, would map this point X to a point in Rn, which we label as t sub a of X, the image under t sub a of X. And so here t sub a, that's capital T sub a is mapping X to t sub a of X. And so here t sub a maps points to points. Same exact function, we're just describing it from a different perspective. You can either think of elements of Rn as being vectors, but literal vectors, and we can think of them, this matrix transformation as mapping vectors to vectors, or instead of describing our elements of Rn as vectors, we can describe them as being points in the space Rn, where those points represent a vector, and then T sub a would map points to points. Points in Rn, the corresponding points in Rm. Okay, and so this is figure 1.8.3 in the book. Okay. Okay, so theorem 1.8.4. Okay, so this is an implication statement. I'm going to illustrate it in this way. So let's say you have that. The map T sub a from Rn to Rm, and T sub b from Rn to Rm are matrix transformations, and T sub a of X is equal to T sub b of X for every vector X in Rn. That statement implies that A equals B. Okay, so theorem 1.8.4 says that if T sub A is from Rn to Rm as a matrix transformation, and T sub B is a matrix transformation from Rn to Rm, are matrix transformations, and T sub A of X equals T sub A of B for every vector X in Rn, well, then that means A equals B. Okay, that's theorem 1.8.4. Okay, so another point. If E1, E2, En are standard basis vectors for Rn in column form, then the standard matrix for a linear transformation T from Rn to Rm is given by the formula A is equal to, equal to this T of E1 because I'm separating the elements, I'm partitioning the set T of E2 and continue the partition in between. And then here, I have T of E. Okay. Okay, so I'm going to denote this as equation 15. Okay, so if E1 to En are standard basis vectors for Rn in column form, then the standard matrix for a linear transformation T from Rn to Rm is given by this formula. Okay, so what is the standard matrix for a linear transformation? It's the matrix that you would left multiply by to define this function T, right? So T is a function where it would be T sub A of X, some matrix capital A. And so what we're doing is we're finding that matrix A that we can think of T as left multiplication by. Okay, so that matrix A, which defines what this T is, you can find it by taking the standard basis vectors for Rn in column form, E1 to En, plug them into T, and the corresponding outputs are the corresponding columns of this matrix A that defines T. So T of E1 is the first column of A, T of E2 is the second column of A, T of E3 is the third column of A, dot, 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 T of En is the nth column of A. So A has n columns. And so that means T of E1 to T of En are all n columns of A. And so that determines the matrix A, which determines T. Okay, so that's what this is saying. Okay, and so next class we will continue with this idea. Okay, so we covered a lot of material today. We are on 1.8 right now. And so I'm going to assign the homework for 1.7 for next class. Okay, so the homework for next class is 1.7. So section 1.7. And so it's the problems from there, from the homework sheets. So let me bring this up for a second here. So now this is 1.7. So it's just numbers 2 and 37 in 1.7. Okay, so 2 and 37. So 2, 37. Wait. Okay. So section 1.7, 2 and 37. So that's the homework for next class, and I'll see you on Tuesday. Okay, there's office hour tomorrow. Have a good night. You too. Have a good night. Have a good weekend.